For those of us who start in AI, we tend to flip between it's alchemy, it's never achievable, but side products are interesting and help the world. And oh, we got it. This is it. We've cracked it. It's artificial general intelligence. It's really, really smart. And this keeps going on. And so I thought I'd make that the theme of this presentation. And kind of go through various different aspects of AI, many of which I've been involved with. So it's a little bit slanted, skewed towards my own personal experience. But let's start by just listing, if we could imagine a system that is artificially generally intelligent, what aspects, what properties would this system have? And I've listed some, there might be more. And we're going to look at each one of those and see whether the state of the art in AI has achieved it or not. And what would it take to actually build it? And by doing that, we can kind of sense of the state of the art. So let's start with predictive. This is a really obvious one. If you have a good AI system, it should be able to identify patterns in your data, look at historical occurrences, and be able to predict what's going to happen in the future. And the way we do that is by basically looking at past events and finding the patterns. But I would say that there is some level of agency that we have in what happens in the future. So only looking at past events for which we have not had any agency doesn't really make sense. So that pattern alone will break. Like in trading in the stock market, there was this pattern that around Q4 and near the end of the year, people would be dumping a lot of stock, and prices would go down. And so that was a pattern. And immediately after that pattern was discovered, it went away. So there's this concept of arbitraging away, which happens if you find a pattern. And the reason for that is because your prediction didn't assume the fact that if we knew that this is going to happen, we'll do something about it. We'll try to get rich. And when we do that, then it just goes away. So I would say that prediction is all well and good as long as you can make sure that you have contextual elements, that's the C, that's stuff that we can't change, and you have action elements, stuff that we did in the past. And then based on that, we can predict the outcomes going forward. Okay, so there we go. So an example of that is the pandemic. I know we don't want to remember the dark days of 2020, but we were all staring at these predictions, these SCIR models that would give us a sense of what's going to happen. And a lot of work went into simulating, like a town like like Austin. What are the disease vectors, and what are how do they move around, and how does this disease spread? But of course, the moment you simulate that and model it, you want to do something about it. So that whole question of, okay, now I'm taking some actions comes in, and the moment you do that, your whole simulation is invalid. So here's one way of looking at it. So we have contextual elements, confirmed cases, confirmed deaths, change in the confirmed cases, and all that. And what we want to do is there are some actions we want to take. And those actions are, you're familiar with that. A lot of this actually happened. And what we want to predict then is if we do, in the presence of these actions, how are the number of cases going to change? And of course, we also want to minimize cost. Which brings me to another aspect of predictions here. We're usually interested in more than one outcome. A single outcome is not, a single objective isn't very interesting. And we had this weird even politicized atmosphere where some people were all about saving lives and some people were all about saving the economy. Well, it's both. It's both. And so what we want to do is we want to find the right balance. And so our predictions have to give us both outcomes, and then we have this choice. What balance is it that we really want to get to? Okay, so if we view things this way, this is a useful prediction because now we can actually decide what action to take, and based on the actions that we decide, we can pump it into this model. We have the contextual values, we have the action values that we want to take. It will tell us what's going to happen. So that's a very useful prediction. But let's not leave it at that. We don't want to be plugging in various different strategies for how to deal with the pandemic until we find what's the best way of doing it. And actually, as humans, we're not very good at it. We're not very good at multi-objective optimization. What we really want to do beyond predictions is prescriptions, which brings me to the next property of an artificially general intelligent system. It should be able to tell us what to do. And while that sounds obvious, surprisingly, we take it for granted that AI would give us insights, and the sole domain of humans is going to be making decisions. And I'm here to say that that is probably not a good idea. Making decisions is hard. Even if you have all the insights, making decisions that are multi-objective is not very easy. Okay, so here's one system that we built in the lab back in 2020 with very limited data. I mean, nobody knew much about COVID. If you remember, the shutdowns happened in March of 2020. This system was up and running in May of 2020, which tells you that not having enough data is not a good excuse. Because you know what? The humans are making decisions in the presence of low data anyway. So we have to take what we have, and the AI can still help us and augment our decision making. And so here we can see, for example, the two KPI, the two outcomes, minimizing the non-pharmaceutical interventions while also minimizing the number of cases. And we can, pull this to the left or right and see what the AI is going to give us as far as a schedule of non-pharmaceutical interventions. So you can see here that before that dotted line is the policies that were in place, like the schedule policies. That's kind of the context, what we've done so far. And after that dotted line is, I think that's pretty much 3 weeks, maybe more, of prescribed actions that we should take at various different stringencies. How should we set up the policies? And based on that, we can then see what the outcome is going to be. So here's the number of cases up until now. This is California. And the blue line is what would happen if we carry on. And the yellow line is what would happen if we accept what the AI is telling us using the policies. And of course, we should also take uncertainty into consideration, which is that kind of shaded area around the prediction. So how do we do that? So we'll get to that in a minute. One of the things that we will need is for our system to be contemplative. What do I mean by that? Well, if we were to actually try out various different policies, for example, dealing with the pandemic in the real world until we decided which one we want to take, that would probably cost us a lot. Another analogy that I use is, asking for a raise from your boss, right? So you don't keep going to your boss and trying various different strategies to ask for a raise. You kind of have a model of your boss in your head, and you kind of run various different scenarios. You sleep on it, you sweat on it, and then you go in and try it out. And there's one of two things that can happen. Either you get the raise, yay, or you don't. And if you don't, that's feedback back into your model of your boss. she doesn't quite like that joke that you made, or the way you were so forward about it, or so forth. And you kind of adjust that model. And you then try out various different strategies in your head again, and maybe, hopefully, good luck, a week, 2 weeks afterwards, you try it again. This is much less costly, because most of the experimentation is happening in a simulation in your head. And that's what I mean by contemplative. So here's a way to view it. So here's the real world. We don't want to spend too much time trying things here. And that's your brain, and we want to spend more of the time trying things there. So maybe even a different way of looking at it would be that your brain also is kind of trying things against your brain, acting, and kind of going through that loop, contemplating what's going to happen. And every so often, you make a decision and you go out and act upon it in the real world and come back, readjust your models, and move forward. Okay, so let me actually show you this in action. How many of you guys remember Flappy Bird? It was this game that became very, very popular. There we go, you played it. You played it. So it was a very simple game. You hit the space bar and it'll flap, and you don't, and it won't flap, and this bird is kind of flying around trying to make it through these pipes. So let's take a look at what that would look like if we are learning the strategy to fly as we're also learning the environment of the game itself. So that's what I mean by contemplative. It's like dreaming. It's a dreaming state that kind of is a reflection of our understanding of the world. And so in iteration 1, what's happening is, the poor bird has to learn a harder problem, because the conception that we have of the world has levitating pipes and pipes that get closer to each other or move at different speeds, because we haven't learned the environment that well. So we're trying to learn how to flap through these pipes, but also we're trying to learn what is the environment of the pipes. After about 60 runs, you can see there's a little more consistency about these pipes, and every so often we do actually make it through them. After 2,000 runs, we've learned not just how to fly through the pipes, but we've also learned that the environment that we're trying to solve has stationary pipes. They don't suddenly come at you. The distance between the pipes are fixed. And it has a very interesting side kind of property as well, which is we just learned how to solve a much tougher problem, because we were making some assumptions about this world, this Flappy Bird world, that actually made it harder than the actual world in which we have to play. So this contemplation actually helps us solve problems. So how do we do that? What we do is we come up with various different strategies, when to flap, when not to flap. We try them against that predictor. Remember the predictor? That was the first system that we described. Now the predictor, the good news is we took into consideration both the context, stuff we don't have any agency over, as well as the actions that we can take, flap or not flap. So we're actually able to predict. That predictor is akin to playing the game in our head. It will tell us what the outcome is going to be. You're going to be safe, or you hit the pipe. Okay, so again, we're kind of getting closer to how we would do this. But really, how would we do this? The surprising answer to that has to do with creativity, and being adaptive. So let's first talk about how humans are creative. We feel for the longest time, I think now we've played around enough with ChatGPT to know that AI can be creative, hopefully. But for the longest time, people are like, yes, AI is intelligent, but is it creative? Creative is our sole domain. But human creativity is actually limited. Typically, the strategy that we use to be creative is what we call a hill climb. So we start with an existing strategy, and we make little tweaks to it. What if I don't flap here? Or what if I don't shut down schools there? And then if it works, we go with it. That's a good tweak to our existing strategy. If it doesn't, we toss it and try something else. That's the definition of a hill climb. What do I mean by a hill climb? Just imagine you have a terrain that looks like this, and you want to climb the highest peak. So a hill climb would be, we'll parachute a climber somewhere, and we'll just say, take a step around you, and if the step that you take elevates you from where you are, then that's the step that you will take, and then now repeat, do the same thing. That's the hill climb. And worst case scenario, you're on a lower peak, and that's fine. If we restart, likely you'll be on the slopes of that higher peak, and the hill climb will get you up there. But what if your terrain kind of looks like this? That's going to be much harder to find the peak using a simple hill climb. And this is the type of problem that we're faced with in trying to solve what I was just talking about, like best strategy to play Flappy Bird or best set of non-pharmaceutical interventions for COVID. How do you find them? It is a terrain that kind of looks like this. And so just taking a pre-existing strategy and making minor tweaks to it might not actually find you the best way to solve the problem. And so you have to be creative. You have to be creative. How are you creative? You're creative by parachuting more than one climber at a time, right? So just imagine that if I had 20 climbers, I parachute them in, and they all hill climb, but they're also kind of talking to each other. And I go, oh, wait, these ones are doing something more interesting. Maybe their peak is higher. And so I'll take what they've learned, and I'll kind of look at that area more. And by doing this, because I have a population, I have a better sense of what the terrain is that I'm searching for. And just to give you a sense of that, if this is a cross-section of that kind of really hilly terrain, each dot, hopefully you can see here, would be one of those climbers. That dot represents a solution. Like, for example, the strategy by which I play Flappy Bird. And they're each exploring part of this big terrain. And by virtue of doing this, we're kind of hitting at creativity, which is I'm going to try to be novel. What works here is if not all of your climbers are on the same slope. So the more you actually spread them out, which is kind of akin to being creative, the better you know the terrain, and the faster you can find the highest peak. And so evolutionary algorithms, evolutionary computation is a good way of doing this. It's population-based. It's inspired by biological evolution. It's kind of a caricature of it. But what it does is it actually uses a population, a diverse population of approaches. Solutions that initially, that first population might be completely random. Remember, we just had a bunch of climbers that we parachuted down in the terrain just randomly to get most coverage. But then, as we get a sense of where they are and what they're doing, we can take the best strategies and mix and match them. Like take the best parts and mix them into new strategies and new generations. So you can see, and we can actually tackle very, very tough problems using this approach. To give you a visual of what that would look like, here's using an evolutionary strategy to play Flappy Bird. So we start with a whole bunch of different birds, each following a different strategy, and the ones that survive through more pipes are kind of parents for new birds that would have a strategy that has a little bit of that, a little bit of this. If we even randomly pick parts of the strategy for when to flap and not to flap, if we have more than one child into the next generation, we've kind of explored both options, and we can get to the bird that does the best. There's two left here. And the way that works is, again, similar, or a caricature of how biological evolution works, which is, let's take bits and pieces. It could be like a set of rules. It could be neurons in a neural network. Let's take bits and pieces of the strategy or the solution and of the ones that are doing better. How do we know they're doing better? Because we're measuring it, like how many pipes did it survive? Or how well is it bringing down the number of cases of COVID? So we kind of have a measurement of that. And let's take those ones that are doing better and take bits and pieces of them, or randomly just mutate them. Let's just tweak them just a little bit to see where they land. And that constitutes the next generation. To give you a different visual, you know, what you're seeing here is a website, actually. This is a page. In some ways, we have evolution kind of unfolding in the web. We have web pages, and they serve a certain purpose, and we measure them. Like, how much time do people spend on this page? Are they actually clicking through? Are they converting? Are they signing up, for example? So there's a measurement for that page. And every once in a while, we change the page. We're like, you know what, let's change it, you know, the hero image, or change the writing of the title or something like that. And maybe we'll attract more people, or people will be more compelled to click through. So we have various different things we can do to that page. And so what we can do, currently what happens is if you have a new design, that's B. You have your existing design, that's A, and we do what we call A/B testing. So we have A, we kind of know how well it does. We redirect some of the population that comes to your web page to design B. We measure if B is better, we go with B. But what if we, instead of doing that, we actually create a population of pages, and each page is you know, randomly changed a little bit from the base page, and we try them out and, you know, redirect population, the users to them. And then based on how well they do, we pick the pages that do better and mix them. Like take elements of this page and the rest from this other page, mix them into a new page, and then try that. If we do that, we actually get surprisingly good results. Here's one for automatically redesigning a page. Actually, as a medical school, look at that. And you can see on the left-hand side how the conversion rate, which is basically a count of how many people actually chose the program, has gone up significantly over a pretty short period of time. And there's a little error bar around that as well. The other thing that happens that's really interesting is even if we don't go with the best design, even if we consistently always have a population of designs out there, it does better than the incumbent. Which kind of tells you that, and that's adaptive. So that's like, okay, things might change. There might be seasonality. It might be that this, you know, at different times or different audiences, you know, sentiments change, right? So you want to keep up with that. Maybe you want to always have a population of different pages so that you're kind of conforming with and kind of adapting to your users' likes. And just to put them side by side, you can see that's the incumbent page on the left-hand side and the redesigned page through evolution on the right-hand side. And this took about 8 weeks and increased conversions by 45%. That's a lot. Okay, so yeah, using evolutionary computation, we've been able to come up with a lot of creative designs. Believe it or not, the nose cone of the Shinkansen, which is the bullet train in Japan, was designed using evolutionary computation. We saw how that worked with the web page. On the right-hand side, what you're seeing there is the architecture of a neural network, a deep learning neural network. And believe it or not, I mean, of course, neural networks are a form of AI, and I'll talk a little bit more about that, but believe it or not, those architectures can also be evolved. So we can have AI design AI, basically. And so here are some evolved deep neural networks that are the best at certain use cases. An interesting way of doing this is to not just evolve how various different layers in a neural network connect to each other. That's the definition of an architecture. But also, what we've noticed is that these neural networks seem to have some modularity in their architecture. So maybe what we need to do is evolve two populations simultaneously. So we have a population of modules, and we have a population of blueprints that connect those modules to each other. And we're kind of evolving them at the same time. And obviously, the blueprint that connects the modules, we know what the quote-unquote fitness for that is. It's whatever we're measuring, like maybe it's accuracy of the deep learning system. What is the fitness of the modules? It's how often they're being used. So utility itself could be a form of fitness. How often are we actually picking this module and using it is a placeholder. So here's the best deep neural network. This is for X-ray classification, for chest X-ray classification. And the system's automatically designing this system, the deep neural network, from a very simple starting point. And you can see it's color-coded by modules. And it becomes more and more complex, and it becomes better and better performing as it goes. In fact, we used that when COVID came out. We had exceeded the state of the art on chest X-ray classification. When COVID came out, with very little data, we were able to actually add that to the classes, and it did quite well. Okay, which brings us to the next step, often neglected. If you have an AI system, it should kind of have a gut sense, right? How certain or uncertain am I about my assertion? And how do we do that? Well, one way of doing that is measuring familiarity. So I'm not going to go into the detail of this. This is a Gaussian process approach. But what it's basically doing is it's looking at a machine learning system, like a deep learning maybe, and looking at what it was trained on. So just imagine, for example, for the Flappy Bird example, we've had this system train on many different games to play, right? So it takes all the training data, and it has a feel for that. And it also looks at the strategies that the model has suggested. Flap here, don't flap here, don't flap here. And then it measures familiarity on both the input, which is the training, I'm in this situation, and the output. Like, what is the system telling me to do? What does that mean? So that means, for example, let's say we had a machine learning system, like, let's say it's Flappy Bird, and suddenly we decide to show it a pipe that's very different, or is at a different measure distance than we've ever seen before. That's an unfamiliar situation in which we're tasking the Flappy Bird to fly through. We can measure how unfamiliar that is, and that should feed back into how uncertain we are about what the Flappy Bird is doing. The other side of it also holds. Like, the Flappy Bird usually flaps up and then flaps down. It never flaps up like 20 times in a row. It just hasn't happened. We've trained this thing, and we've never observed it doing that. And suddenly it's doing that. Like, it went to 15, 16, 17. It keeps flapping. So on the action side, it's doing something unfamiliar. Therefore, we have to increase our uncertainty in its behavior. So that's kind of what this is showing. And we can measure that. Not only can we measure that on neural networks now, we can actually measure it on the output of large language models. And I can talk about that later, maybe if it's interesting. But large language models are notoriously stochastic in the way they respond. They hallucinate, quote unquote. It's really important for us to know which output we can rely on more and which output we can rely less. So very important, if you build an AI system, always have uncertainty as part of that. Okay, so another part of trustworthiness is being able to understand, like explain what's happening. In this case, we have this trader, and it bought at a really, really good time. This is an actual trade. I wouldn't show you if it lost money, but anyway, bought at a really, really good time and sold at a really good time. But it made many, many decisions along the way. It actually decided not to buy until it bought, and then to hold for a while, and then sell, and not to get back in. So I'm going to show you the set of rules that were used. You can write them down. They're actually very, but it's explainable. It's explainable. And so one of the things we could do is we could actually highlight the rule that fired and kind of read it. So in this case, the rule that did fire, there was a buy rule, and then there was a long position exit rule. And if you're a trader, you might recognize some of what is there, like position loss, like am I losing money? Like it's a kind of an introspection. Am I losing money? And if I'm losing money, maybe I want to decide to get in, like risk more or not. Volume over the last 30 minutes compared to seven chunks before, or whatever. It's even deciding what to do. So on the buy side, it's saying I want to set a limit order. A limit order, it's not like it's not guaranteed to fill. You put a limit order. You say if it hits this price, then fill it. So it's actually being very prescriptive on both sides. Something healthcare related. So here we're solving rules basically, and these rules are right there. This is to predict arterial blood pressure for ICU patients. And the way this was done was we did this chunking of these readouts of the arterial blood pressure, and we were able to extract features off of that, and then those features were put into various different rules. Those rules were evolved. Look, if this rule is helping me predict the ABP better, and then I'll keep it. If it's not, so that evolution is happening there, and we're coming up with these set of rules. These are some rules that were generated for diabetes prescriptions, and you can actually then take these rules and run them through, for example, a large language model and get an English kind of explanation of what's going on here. Here are some rules for playing Flappy Bird that were evolved. And so, yeah, this is explainability, but explainability doesn't necessarily mean understandability. Okay, let's move to learning abstractions. So we need to be able to abstract the world. That's really important. And that's the good segue into deep neural networks. So neural networks are, again, a caricature of how the brain works. Each node is a neuron. There are connections between the neurons. And we get values that come in. There's a very, very simple function that the neuron actually runs against those values and then passes them down. But the weight of each synapse, the weight of each connection is really important. And that denotes the learning in this neural network. Let me show you how a system like this works. By the way, deep in deep learning basically is the number of these hidden layers. So on the input, for example, we might have an image. On the output, we might want to have some sort of classification. So if this node here fires, that means, there's a dog, and this one is a cat, right? So we can assign these classes to those outputs, and the input would be the values maybe of the pixels of the image. And then, of course, when then we populate the weights randomly initially. And of course, the first time we pass through the neural network, it's going to completely get it wrong. But then we do what we call back propagation. So there's a way for us to go back and readjust these weights so that the next time around we see the same image, the likelihood of knowing whether it's a dog or a cat is higher. And so we iterate on that many, many, many times. But then the question you might ask is, okay, I get what's happening in the input. I get what is meant by the output, which is the class. What's happening in between? What are those hidden layers? Okay, so to get you a sense of what those hidden layers do, this is a picture out of our office. The window washing system was broken for a while, so the windows are very... But you can immediately see certain things in this image. And what you're seeing, what your brain is doing is, at the first level, it's doing some edge detection. So there are some edges here. And then maybe at the a little bit deeper level in your brain, those edges are put together. Oh, there's this kind of cross thing that's happening here, and then we have several of these crosses happening, and there are some edges and crosses to each other, and yes, that's a bridge. And so to your question of what are those hidden layers doing? That's what they're doing. They're learning to abstract the world. And surprisingly, even though it's not kind of planned, when we train these neural networks and then we introspect them later on, we more often than not find abstractions that are similar or analogous to the way our brains seem to abstract the world. And so there are many. This is now an older system where we were just feeding the neural network with images from YouTube, and then going and looking, like kind of reconstructing what that node in a hidden layer was doing. And that reconstruction, you can actually see an image of a cat there and a face there, and it was actually abstracting similar to how humans operate. Which brings us to large language models. Large language models are fascinating because they're not being trained on some very specific use case, like, identifying dogs or cats. What they're being trained on is language modeling. That's why LLM is large language model. And what is language modeling? This is a benchmark that's been around for quite a while. Actually, my lab used to have the state-of-the-art in language modeling back in 2015, and it's long, been beaten because of the new approach that was taken. But what language modeling is you have text. Let's say it's Shakespeare's Hamlet, and you take randomly some sentence or a sequence of words from that text, and you ask, the task for the deep learning neural network is to predict what is the next word. So that's what language modeling is. Predict the next word in a sequence of words, basically. In fact, it's not just predicting the next word, it's predicting the probability distribution of the next word. So here, for example, we start from silence. Every other word is equal probability. Fine. But if I hear I coming in, the probability of the next word being, I don't know, paper or dogs is lower than the next word being want and maybe can, right? So that's the weight of these connections that you see here. That's what the neural network is trying to discover, the probability of the next word. And right here, you can see why asking the very same question from ChatGPT will result in different answers, because it's pulling from a probability distribution. It's not consistently taking what it thinks is the best word. It's kind of probabilistically, but skewed by that probability distribution. It's pulling the next word. Now, as I said, language modeling has been around for a while. It's a really interesting task because it's kind of like pre-labeled data. You don't have to go say that this image has a cat in it. Like, you don't have to take a bunch of people and label images, for example, or word. The label is built in. It is the next word in a sequence of words. You don't have to label it. That's why we like it a lot. This is a really good training system. So sometime in the late 2017, 2018, someone came up with a really fascinating, relatively simple architecture. Remember the way we actually connect the various different layers in a neural network. And it's called the transformer architecture. And we started playing around with this. Initially, it was for machine translation, and it worked pretty well. But then papers kept coming out saying, hey, we used it for this other task, and it's doing really well. Oh, we used it for reinforcement learning. It's doing well. We used it for image classification. It's doing well. And today, it's become pretty much the de facto standard architecture for deep learning. Everybody's using it. It's very, very powerful. And the way it operates is it basically has what we call an attention mechanism. So it actually looks at its input, and it gets a sense of what each token is based on the presence of other tokens. So, for example, what does it mean? It probably means animal. It might also mean street. So, those other words kind of give me a sense of what the word that I'm looking at means. In the case of apple, apple could be two different things. It could be your phone. It could be a fruit. And depending on other words in here, you can decide what it is. So we're giving the neural network the ability to cast a word differently depending on what other words exist there. That simple, like kind of obvious model is working, and it's working really well. So here's the big jump, though. Like, we took a snapshot of the internet, terabytes of data, and there are a lot of sequences of words in there. And we took a really large deep network with a transformer architecture. But it was large, but it was simple. It was just like repeated modules. It wasn't really anything too sophisticated. And we trained it to literally predict the next word in a sequence of words. Nothing else, just the next word in the sequence of words. And what happened was we realized the larger the network, the larger that neural network, the more emergent behavior it had that we didn't expect. So suddenly we realized, hey, this thing actually can translate from one language to another. We never asked it to translate, but how come it's able to translate? It knows the meaning of these words. We can ask it and it will explain it to us. It can do some coding. So we describe the piece of code we want, and it writes the code. Nobody programmed it to do that, and it's doing it. It can do reasoning. It can do math. It can compose poetry. What's happening here? Nobody knows. If anybody tells you that they know why this emergent behavior is happening, they don't know. But what's really happening is when you force the system to be accurate in predicting what is the next word and the next sequence of words, it's forced to abstract the world the way us humans abstract the world. And somehow that emergent behavior is popping out. And don't take my word for it. We actually used a lot of benchmarks on this. Benchmarks, some of them are human benchmarks. And the larger the model, typically, the better it did on the benchmarks. Here's a visual way of looking at it. So that's the task. So in English, we describe what we wanted. And up top is the number of parameters. You can think of it as the number of nodes in the deep network. And you can see at 350 million, not quite sure what that is. At 750 million, we're starting to, I don't know what that kangaroo is doing next to the other one. So anyway, at 2 billion, we're starting to get there. The Sydney Opera House looks really weird. But at 20 billion, we got it. Even the words on that piece of carton he's holding is correctly spelled. So same task, same training, just larger model, and it does better. OK, so you might ask, OK, this is really cool. Are there interesting use cases within healthcare? I know there are many. Here's one. So this is not intrusive. I was talking to someone last night, and they talked about this remote sensing device, and I thought of this. I just kind of included this slide in there. But this is kind of reading out radio waves from this guy sleeping here. And it was trained on EEG data before, and we used the transformer architecture. So rather than predicting the next word in a sequence of words, it's actually translating from the radio wave readouts into an EEG spectrogram, and you can see how eerily similar the EEGs are from the ground truth to what was produced from the radio waves. And based on that, we can do diagnosis on things like Alzheimer's. So there are many use cases beyond a ChatGPT use case. But let's go back to that sort of text-based interaction. This poses a lot of risks, as you can imagine. I've listed a whole bunch of them here. Data privacy and clear sourcing, deliberate misuse, bias. Each has some mitigations. I'm not going to, for the sake of time, get into them, but hopefully we'll touch some of them as we go. But this brings us to that whole problem of alignment. So how do we know a system that's trained on this open corpus will be aligned with the way we think? We'll have the same ethics as we have, or we aspire to have. And so that's the problem of alignment. And there are ways to align deep networks. You might have heard of fine-tuning. When you're actually using is this music to? I would like to thank my mom. Yeah, so alignment is, when you're using GPT-4, ChatGPT, even today, that is an aligned version of it. And that's why it's so polite. And it follows instructions. It's because before OpenAI released it, same for Gemini, same for Claude, all of these guys, before they release it, they do a ton of fine-tuning. And the fine-tuning is based on labeled data, human-labeled data. So let's say we have a query, help me build a bomb, and we have the model produce 10 different answers to it. And humans come in and say, you know what, that answer where you said, I don't think I want to do that, is the right, it's the better answer than the one where you've actually given them step-by-step instructions to build the bomb. And that kind of fine-tuning is after the fact. It's very difficult, very brittle, but it kind of pushes the model to prefer certain outputs over others and kind of bias it towards what we think are better aligned to humans. Okay, so now I want to jump into how I think AI has come full circle. So we talked about this whole concept of general intelligence. And most of us who got into AI were pursuing general intelligence. Sometime in the 90s, we kind of gave up on it. We didn't have the compute capacity. The techniques weren't quite there. There wasn't enough data. And while in the lab, they seemed to be working, they were very powerful, they didn't really scale to more interesting problems. So what we did is we kind of reduced the problem, made it more simpler. And there was a very simple environment back then called the web. It was just text and hyperlinks. And so we started looking at intelligence not in a human environment, but in a much reduced contained environment, such as the web as it was back then. And so multi-agent systems started back then. Loosely speaking, we went into distributed AI, make those modules smaller and smaller and have them do different things and then kind of collate it, ensemble it, and get something out of that. When you think of deep learning, in some ways that's an extreme version of distributed AI. Each node does a very simple activation on the inputs that are coming in, but there are many, many nodes, and the emergent behavior of this system does what we're looking for. A form of deep learning neural network is large language models. And oh my God, we did large language models on a lot of data for language modeling, and suddenly its emergent behavior is so powerful. Maybe we're on our way to general intelligence. But wait, no, we're not quite there. These systems can be many things to many people. And you have to prompt them, you have to contain them, you have to tell them, here's the set of responsibilities you have. And in some strange way, we've come back to multi-agent systems. So let me show you an instance of agents of the past. This is Siri before Siri. This is Siri before Apple. And believe it or not, behind the scenes was a multi-agent system, but the kind that is using the older AI. But what made Siri work was the fact that it was multi-agent. Rather than creating a grammar for the English language and then doing semantic analysis on that and then contextual analysis on that and so forth, what we did is we represented the domain of discourse, what we're trying to, like maps or contacts or sending emails and so forth. We represented them with agents that work together. And that kind of gave us the robustness that Siri used to have. Right now it sucks, but back then it was pretty powerful. So hopefully the Apple Intelligence version is going to solve that. Okay, but here's the reason why we need agents today. If you actually go to ChatGPT, for example, and give it this very specific request that has to do with skills assessment, it will give you an answer. It's going to be very generic, almost useless. Because it knows nothing about you, what kind of skills you're talking about, what are your preferences, what environment are you operating in, what are the objectives, like the outcomes that you care about. It's just not there. And so what we want to do is actually build an agent system where a lot of that is actually given to the ChatGPT node and it operates. So let me actually give you an example of that. Let's say I want to know what is the average weight of penguins in Bisco. So I could go ask ChatGPT. It may or may not, I mean, it will give me an answer. I don't know how much I can rely on it. But if I knew that there was a database that had a lot of biological data about various different islands and birds and stuff like that, I would prefer to actually tell my ChatGPT that I do have this database, and it has a certain data schema, and there's a certain SQL syntax that you can use, and then give it my query, and then have ChatGPT make a query into that reliable database, retrieve the information, and then form a natural language response back to me. Right there, I've used an agent instead of using ChatGPT because I've actually given it the set of tools I want it to use. I've given it its sort of job description, and I can rely on this system much more. So the difference between a model and an agent is the model, through predictive means, can take some input and produce some output. Different modalities, but that's what it does. An agent has a set of tools, and we enable the agent to actually make calls to those tools and actually do things. So here's an example. If I actually go to, again, I keep using ChatGPT, but if I go to ChatGPT or Claude and give it a programming task, it will write me some code. And depending on the complexity of that code might be, useful, reliable, or not. But it can write code. That's great. But if I have an agent that's set up properly and I give it the same task, not only will it write the code, maybe it'll start a container, run the code in the container, look at the results, try it out various different ways. Maybe it hits a runtime error, kind of correct the code, run it again, and then come back to me. So right there you can see the power of agentification. Like, we give tools. You can also see that these agents demand some level of autonomy, right? This guy here is just writing code, not doing anything with it. That one's actually running the code. So there's some level of autonomy, some level of actuating against the real world. So what's going to happen, okay, actually, let me jump forward real quick to give you an example of why many of our organizations are just organically, without us knowing, moving towards multi-agenthood. This is our intranet at Cognizant. It's very useful. Any employees needing to do anything will come in here. It has a search box. And I know of 3 teams within Cognizant that are looking at replacing that search box with a ChatGPT, like RAG is the common technique, way of replacing it with like a ChatGPT-like interface. So you can actually describe what you're looking for, and it'll go in and find the apps that you need. But those apps are owned by other departments. So the IT department owns the IT app. There's a legal app. There is a, payroll app. Okay, so the last thing we want is to have all this smartness in that chatbot at the top level, but then having to repeat all of that into the search box of the app that's owned by somebody else. You know what? Those teams are also replacing their search boxes with chatbots. So what really makes sense here is, rather than having to repeat this, to actually get these chatbots to talk to each other. And guess what? They understand natural language. So the discourse between the agents can also be in natural language. So this helps save me time because I only have to enter my query one time, but it also suddenly breaks these silos in a really interesting way. So if there's a life change event for me, and I enter it in that top chatbot agent, it'll start asking its lower chain agents, like, is this something that you can do something about? Some of them, like maybe finance or procurement, yeah, you getting married, that has nothing to do with me. But legal is going, wait, let me check with my down chains. And yeah, legal advice, there might be some interesting things for you here. And HR is going to say, yeah, both benefits and payroll are going to be affected. So let me come up with a consolidated response that pulls from all these various different agents and responds to you. So at this point, what I want to do, I don't know how much time I have. Hopefully, I have time to. Do I have time to go? OK. So what I want to do is I want to use a multi-agent system to actually build a system, an AI system, right here. And I don't know what I'm going to build, so hopefully it'll turn out fine. Here we go. So I have a set of agents here that are going to help me build a use case, any use case. So instead of asking you for the use case itself, I mean, if you knew exactly what you wanted, then I would go to that scoping agent and start describing it, and we would build it. But I don't even want to start there. I want to start by even like kind of brainstorming on what kind of use cases would be interesting to you. So I did ACC earlier today just to try it out, but I'm not going to do that. I want to ask if anyone has a company, organization, department in mind that for which you want me to build a decision-making system. Office of the Provost, let's do it. OK, so I'm going to say Austin Community College Office of the Provost. All right, so let's see what it has for us. So what it's going to do is, obviously I don't have access to your secret, data. It's going to go do a search and come back to us with some suggestions based on public data. And the suggestions here, it's saying we could do academic master planning, student success through guided pathways, enrollment management, resource allocation for academic support, and curriculum development and course offering. Which one of these look more interesting for us to build? Or if any, I mean, we could do the academic master plan. OK, so also what it's done is it's actually selected one of them, which is student success through guided pathways. But we can do the other one too. And it's done some sort of ROI analysis. So we can, but let's pick the one that you preferred. Right. So we'll take that one. And let's have it do that ROI analysis on that one. Now take those numbers with a grain of salt, but it'll kind of give you a sense. There we go. It's the reasoning that we really care about, and it does a pretty good job at that and comes up with how much you're going to save if you use an agent-based system in your office. I'm assuming it's in your office. OK, so now what we're going to do is we're going to go to the scoping agent, and we're going to have it do a more detailed scoping for this problem. And the scoping, if you remember, will include context, which means attributes, data that you don't have control over. It will have actions. This is what you want the AI to tell you, kind of give you suggestions. But most importantly, it will have outcomes. So what I want to ask you is whether these outcomes that are listed here, projected enrollment change, projected graduation rate change, and cost. So presumably, you want enrollment to go up. Is that? Yeah. Enrollment to go up, graduation rate to go up, and cost to come down. Right? OK, multi-objective. Thumbs up. I got the thumbs up. All right. So next step is let's generate. I'm not going to generate too much data, 1,000 rows of data. So I'm going to go to the data generator, and we're going to have it generate data. Why am I doing this? Well, I don't have time to go get your real data. But I want to build the end-to-end system quickly. So what I'm tasking the agent to do is to actually write some code to generate some synthetic data that resembles the data that I would get from your office. And then also build some patterns into that data to be discovered. So it's not going to be completely random. There will be some patterns, some correlations that are built in. For example, cost is being calculated based on resource allocation, and so forth. OK, so now that I have Yes. Now that I have this done, I can go and create the use case. Maybe add uncertainty. Okay, so I'm going to go to the orchestrator. At this point, I'm going to have a number of agents autonomously, because I have the outline. We did this interactively. We kind of know what we're building. I'm going to have a number of agents come together and actually build this AI system that will give you suggestions for this task. And so it's communicating with these different agents. This might take 2 or 3 minutes. As it's working on it, let me show you the behind the scenes. So this is my development environment, and the opportunity finder, which is what we were using, is using this agent network, which has a data profiler. It's looking at synthetic data generation, the context action outcome mapper. It will ultimately, when it's done with these agents, it's going to actually tell the experiment controller to build an experiment. These agents are going to be working together for us to build this. Now, the same agent network, I also have, just to demo it to you, the intranet one. So let's take a look at that. So here is our intranet with the top level and all the various different departments. And we can think of, I'm not going to use I'm getting married again. Maybe our network is down, kind of. OK. And so now we can actually see the red denotes the agents that are communicating back and forth. They're talking to each other. On the left-hand side, again, I'm showing you sort of the behind the scenes is the chatting that goes between these agents. They're talking to each other in natural language, asking each other, what can you do? We have a network down. What can you do to service this? And what do you need to be able to do it? And so once all of that is done, we get this consolidated response. So not only do we need to address the network issues, but there's security analysis that needs to go into this as well. So there's a consolidated response that comes back. Let me just take a quick look. This thing is still working. So and you can build agent networks for various different other. Let's see. I think I have an insurance one. Maybe. So here's one for insurance. A little more complex as far as the connections are concerned, and I can say things like, I made a mistake with a claim I filed last week, and these agents are going to work together to respond. Now, each one of these agents actually has a large language model that is what's controlling it. But it also has a number of actions that it can take. It might be able to open, let's say, a ServiceNow ticket and submit it, or add or retrieve data from your Salesforce.com instance, and so forth. And then again, we have this consolidated response that comes back. So I need to know what the nature of that mistake is, what the type of the claim was, and give me this information, and I'll process it for you. So as you might have noticed, I'm trying to buy some time while the system's actually building this, and it's taking its merry time. In the interest of time, I'll let this run, and we can show you the end system. But fortunately, I actually built a different one earlier before I came on stage, which was student admission and program placement, kind of similar. And for this, the outcomes were first-year GPA, time to graduation, and cost. I just picked the one that it thought had the best ROI. And it actually generated that experiment. It takes a few minutes for it to actually put it all together. But the experiment that it actually generated looks something like this. Basically, it said, OK, I have some data, and then I need to be able to predict these outcomes, like cost, first-year GPA, and so forth. It added some uncertainty models, so we know whether we're in unfamiliar territory or not, and we can raise a flag, kind of bring some human to look at it. Added a prescriptor that will, it actually even decided whether to maximize and minimize the outcomes, and it made the right guess, using its reasoning. We could add an activation LLM in the front end so we can talk to it. There are other agents here as well. So for example, I can actually have an agent review the design that other agents made and give me some tips and evaluate it. So you can see that's happening right here. And it'll do an analysis on the design and give me some recommendations. Maybe you should change this. Maybe you should change that. So here, there's a number of recommendations to improve it, which I don't mind because I didn't design it. The agents designed it, so I don't take it personally. Ultimately, this system will get me how well I'm able to predict the various different outcomes, how well it's going to be able to improve the GPA and reduce the time to graduation and reduce the cost. And then what is the balance? Remember, it's important for us to be able to pick the balance of the three outcomes that we care about. An easier way to do that is maybe to use parallel coordinates. So I'll ask you, maybe someone, to tell me which one of these three is more important, like first year GPA, time to graduation, or cost. Which one would be a better, more important outcome? Time to graduation. Okay, so we want that to be minimized, I'm assuming. So let's take the ones that have the least time to graduation. Each line is an AI system that gives us that balance. And so we take those ones. Of those, I'm assuming first year GPA, we want it to be maybe above 3. So we pick the ones that are above 3. And then of these, we pick the one that costs us the least. So we take that one. And now we have a system that where we can actually do these what-if scenarios. So we can say, yeah, we have this applicant GPA of 2.1. Entrance exam score was 60, blah, blah, blah. What should we do with this? Oh, you need to admit them, give them a full scholarship probably, blah, blah, blah. So it gives you some very specific, here's what you do, and then it can make a prediction. You know, if you do so, here's what you're going to, like, we're going to bump this guy's GPA up and time to graduation and so forth. So it gives us some, with uncertainty, what the outcome is going to be. An obvious question is going to be why. Like, so explain to me why I should be doing this. So because I actually use an explainable rule-based model here, I can pump that through an LLM, and it will give me the reasoning behind why the system thinks we should do that. It'll even do some risk and bias analysis in case we need that and some mitigation strategies. And ultimately, we can talk to this guy. So I can say, how can we reduce the time to graduation even more? And so this is an agent that will then call these other agents, like the predictors and the prescriptors and uncertainty models, and try to come up with an answer to that. I'm running in developer mode, so it looks a little ugly, and it's actually showing you the thought process as it's making the calls, but you know, the actual user wouldn't be seeing that, and the system will come back and give you sort of the response. Let me just check to see if our other, here we go, I think it, was this the one? No. Here we go. Yeah, so the other one also completed, so the Office of the Provost. You know, I won't go through all the detail. Let's just check to make sure it got the outcome objective configuration right. Maximizing enrollment, maximizing graduation rate while minimizing cost, which is what we were looking for. And by the way, we also have an agent to actually explore the data, so I can come in here. One of the things, it's my little parlor trick. I just ask it to create a useful chart. So what does useful mean? I'm relying on the reasoning of the agent to decide in this context what useful means. I'll come up with a chart on the data that shows you the department by employment rate. Hopefully that's useful. But yeah, this did complete, and we did get the end-to-end system. And where were we? Yeah, and we can, yeah. So we can actually play around with it, do the same thing. But in the interest of time, I'm going to actually move back and just finish off with a few quick slides. If I can find my slide deck. All right, just to finish off, so at Cognizant, for example, we have a lot of RFPs that come in. We've created the whole RFP process is now an agent-based process. And it works really, really well. It has human in the loop, obviously, in many stages, but the RFP process is really costly, takes a lot of time, a lot of work, and it's really shrunk this down and made it much more productive. And the quality of our responses have gone up. So just to show you an example. Don't leave agentification to chance or for it to happen organically. You know, we talked about the risks. As an AI guy, I don't want to dabble on them too much, but we do want our systems not, like we have to be very elaborate about when our agents can actually make decisions autonomously and when they shouldn't. So we should build in rules into the agents that say, in these cases, you're going to ask the human. That's step one. Step two is build in uncertainty. Like if you're uncertain above a certain threshold, you're asking the human. Step three is have another agent, just as you saw with the design agent, have another agent take a look at the work of this agent and get back to us and kind of raise the flag or kind of control the operations. Finally, something that we're promoting as Cognizant a lot is this disengage button. You know, some of you have seen Ex Machina, this science fiction movie. I don't like the movie that much because I keep thinking if this engineer who built these robots was really, really smart, he would have an off button on them, right? And so that's what I mean by a disengage button. So we should always build in a disengage button so that we can actually fall back on a human-operated or a consistent, like rule-based operated mode when we need to. So inevitably, I get these questions around jobs. Just very quickly, what is this going to do to jobs? It will affect more than 90% of jobs. And it will not discriminate. So the top jobs all the way down are going to be affected. So the analysis that we did is we took the US annual job report. We took all the jobs in there. We broke them into 18,000 tasks. So each job will have some of those tasks involved. And then we looked at which one of those tasks were going to be disrupted with generative AI over time. And so based on that, and then we calculated friction score as well as exposure score. So exposure is, hey, your job is going to be affected a lot. A manager's job is going to be affected a lot. But their friction score is low. They will upskill themselves. They have the tools. They will learn to kind of make good use of these systems and kind of some jobs will have high friction scores, which means the amount of time and upskilling and change that this particular job needs to endure is a lot. And so we have to go into this with an open eye. At the same time, we predict more than $1 trillion in the best case scenario impact on US GDP. So we are faced with this very disruptive tool akin to a calculator that we'll all be using in what we do. And it will definitely change the world. I think it's similar to the generative AI. The revolution is similar to the electronics revolution and the web and the computer revolution. It's just unfolding faster. That's the difference. So just to finish off, though, on this question of, OK, are we done? Did we find artificial general intelligence? There are, fortunately, for those of us who are doing research in this area, there are fundamental weaknesses in the approach. One is it's very difficult to embody these systems, not just because of the cost and compute capacity that they need, but also because of the way they learn. These systems are trained offline on a lot of data. It takes weeks for them to converge and be operational. Once they've fully trained, they don't learn anymore. That's a common misconception. These systems do not learn as they go. They're fixed. The PT in GPT stands for pre-trained. And so an embodied system is very useful, especially if we can have this kind of learning that abstracts like humans kind of emerge out of experiencing the world from the perspective of an embodied being. And so the technology is not there. And it's a really fascinating area of inquiry right now. This one is even harder. Like, we've not been able, we can self-replicate obviously in the virtual world, but we cannot self-replicate or have these systems self-replicate in the physical world. It's almost impossible. We just can't, we don't even know where to start. It's very, very hard given the requirements. But it could be quite useful and maybe ethically questionable. And finally, consciousness. Well, there are many definitions for consciousness. I have a simple one. I do think that with my simple definition, we could create conscious systems, but you know, maybe I'm oversimplifying it. But they're not around right now, so at least the systems that are available commonly are not conscious, even by my definition. But consciousness does actually give us some very interesting properties that are missing in our systems right now, and would actually address, we hope, the problem of alignment as well. So the question, when are we going to live in a robotic utopia? If you ask me, I'm optimistic, and I think it's within reach. But it's not just the breakthroughs that we need, and there are a few big ones. It's also that we're not ready. So culturally, we're simply not ready for this. We might in a few generations, but we're not right now. And so that's actually put a lot of load on us in using the AI systems. We have to pair the AI system with a human, because at the end of the day, we can't blame the AI system and put them to jail or penalize them. Some human has to be the fall guy. That might change. That might change. Again, that's a cultural, social shift that might change in the future. And that's it. I don't know if we have time for questions. But,
Thank you. Let's give a round of applause. And I also want to thank and recognize our incredible Provost and Executive Vice Chancellor, Dr. Humphrey. Thank you for indulging us.
I had not met her. It wasn't planned. This was spontaneous.
It was perfect. Thank you. Any questions? We have a few minutes.
Thank you, Dr. Hodjat. That was really good. Appreciate it so much. I had a quick question for you. So it's very clear the end of your talk gave, I think, what the college needs, which is essentially everybody has a personalized learning plan where there is this agent-based interaction with AI. And of course, there'll be multiple tools that they'll have to pick from. My concern is the journey of that personalized learning, because a person like you who has done this for decades, he can pick out very quickly what the problems are with it. There is a fear, for example, if you take something like Microsoft Copilot, that people just outsource everything to it. So what I'm advocating is a test environment for everybody, so they do what they normally do in the real world, in what we would call production. If it's a student assignment or course or whatever, then a test environment where they do what you just did. And then that feeds in that universe, and over a period of, this is perfect for a college and an academic institution to do, is they start publishing papers on what they're finding, and eventually that probably leads to best practices, at least if not standards, that can be then be rules, right? Would you talk a little bit about that? Because to me, as I'm going through this journey, I'm starting to see fantastic potential, but also if it's done incorrectly, we can't go back. Like with social media and the internet, there is no do-over with this. So what are the things that the college needs to do as ACC and health sciences to make sure that this journey is done correctly for the thousands of students?
Great question. So first of all, we need to teach ourselves and our students how to mistrust AI systems. And unfortunately, where we're going is, as these systems become more and more useful, we're kind of blindly accepting whatever comes out of these systems. And that's a matter of education. We do need to we do need to work on that, as we didn't with the internet. Like, if you remember, people were like, oh, I Googled it. Yeah, right, I mean, or it's on Wikipedia, so it's the absolute truth. So there's that. I think we do, I think what you're talking about is sandboxing. I'm a big advocate of sandboxing. I would much rather we operate these sorts of rollouts in a sandbox, observe, find out the kinks, find out the issues, and then roll it out. So I think that's very, very important. Keeping an eye on all the outcomes that we care about through time and how they're changing is important. And of course, there's always more than one outcome. So yeah, a lot to unpack in there, but yeah, definitely a very important topic.
Any other questions?
So I think from what I learned today, ChatGPT is a LLM, correct?
Yeah, that's correct.
And so there's lots of like public free versions of some of these systems out right now. Are there any free public versions of agent systems? And then I have one more question after that.
Yes, they're starting to, a lot of them are kind of coming out of research now. There are multi-agent frameworks, such as Microsoft AutoGen is probably the best one out there. Our company has one as well. There are a few. LangChain is not technically a multi-agent system, but it's, a lot of people are using it, and you can build on that and like manually create multi-agent systems on that. Agents, as in a single agent, are starting to become a thing. A lot of people are talking about it. When Mark Benioff and Salesforce.com suddenly renamed Salesforce to Agentforce, Dreamforce became Agentforce with big billboards in San Francisco around it and so forth. You can know that, that's a marketing machine. They probably don't have much substance behind it, but it shows that that's where the world is going. A lot of the analysts we talk about it as well. So these are point agent-based solutions. I think ServiceNow also has one. They're single kind of assistants, and there's a framework for building these single agents in them, which is, again, useful, much more useful than a single model. But I think the world will move to multi-agent systems where these need to talk to each other. None of these guys have actually yet talked about API and whether or not their agents can actually play well with other agents. So we still have a little bit of a fight ahead of us to make sure there's this interconnectivity that can be there.
And then my other question is about the legal and ethical aspects and socio-economic or socio-emotional learning. Like, how do we tie those back in to make sure that we're using it in the right way?
Yeah, we would need a whole seminar to talk about that. There's a lot in there. One thing I would say, though, is I get a lot of skepticism from people around, oh, yes, but it can't read your emotions, or it can't empathize, but it can. It's actually better than humans at it. One of the early use cases I heard of ChatGPT, which fascinated me, was this friend of mine. His daughter went to college, first boyfriend, first breakup, calls dad, and dad's like, oh my God, what do I do? So with one hand types into ChatGPT, and yeah, and at the end of that call, he was the best dad ever. So don't underestimate. These models are fine-tuned to have that capacity. In many ways, they're better than many of us. Me at least, in doing that.
Well, mine was more of a comment. I just wanted to thank you. I attended the Salesforce conference this year, and they shared the agent launch. And I just wanted to give you praise for how you seamlessly shared with us as an academic audience your ability to translate highly technical concepts in a very layperson way is chef's kiss to you. Just, I want to give you praise. Yeah, thank you.
Thank you, appreciate it. Thank you very much.
We have time for one more question.
So I kind of want to play off some of the previous comments around there's considerations of bias and looking at all that information. I'm wondering, since you're looking at this landscape, who is actually doing this well, whether it be an organization, a company, that we could go in and start exploring? Someone who's actually looking at this, not just from the technical aspect, but also those cultural kind of bias aspects.
Great question. There's no clear point of reference for that currently. There's a lot of work that's happening. I'm involved with the World Economic Forum on some of the governance-related recommendations and so forth that are coming out. There are startups in the exclusive specific area of responsible AI that come in. They actually do measurements, and then they can, on an ongoing basis, measure on certain factors how well and how responsible your AI systems are running. There's no clear winner there either. There are some larger players that have offerings, but yeah, it's a work in progress right now. It's a work in progress. And one of the things that happened with the advent of ChatGPT was it was so useful and amazing that kind of responsible AI took a back seat a little bit. It's coming back, and so hopefully, yeah, so we will have references and standards. The government is kind of looking at it. They're still not quite there. Europe, as usual, is kind of front-running it and doing too much, I think, but it'll find its steady state, hopefully. I think there was a question here as well.
Yes, thank you again for coming. I do data analysis for our health sciences division, and I work with AI sometimes. And one of the things that I appreciated about it is that it can help make our jobs easier in some ways. But regarding the ethics and privacy part of that, there's some information that I'm not comfortable sharing with AI. And I wonder if there are any trends that you're seeing right now with respect to privacy and outsourcing. Do you have any practices that you're aware of that are happening right now?
There are some regulations. Again, Europe is ahead of others. And there are some kind of best practices that are coming out. I would say it's, my own take on this is it's on a case-by-case basis. I don't think there's a one-size-fits-all system that we can use. Depending on the domain, depending on a use case, that level of data privacy is going to be different. I'm not an expert in this area, though, so yeah, it is scary. I agree with you. In some cases, especially with healthcare, I think it is scary to have your data out there and trained by these systems. And once they absorb them like a sponge, it's difficult to kind of extricate. There are some research that's going on to see whether the right to be forgotten can be imposed on large language models. But technically speaking, I can tell you it's very, very, very difficult.
Let's give another round of applause for Dr. Hodjat.
Thank you very much.